Intro Chemistry, Molar Volume of Hydrogen. In the Charles Law experiment, we studied the relationship between volume of a gas and Kelvin temperature. We saw that volume is directly proportional to Kelvin temperature at constant pressure and number of moles. For example, if we had 20 milliliters of gas at 200 Kelvin and we doubled the Kelvin temperature to 400 Kelvin, we know that the volume would double from 20 mils, it would go up to 40 mils. Similarly, if we started with 20 mils of gas at 200 Kelvin, 20 mils at 200 Kelvin, and we decreased the temperature by a factor of 2, we cooled it to 100 Kelvin, we know that the volume would decrease by a factor of 2 down to 10 mils. And so we were able to solve problems involving temperature and volume using simple logical statements like this one. At 100 Kelvin, a gas volume is 10 mils, and at 300 Kelvin, the gas volume is X mils. We want to solve for mils, so start with mils and multiply by a ratio of Kelvin temperatures that makes sense. It makes sense that the volume is going to increase because the temperature is increasing. So put the larger number over the smaller number. The units of temperature will cancel. The unit you start with is the unit you finish with. 10 mils heated to 300 Kelvin becomes 30 mils. Volume and temperature both increased by a factor of 3 because they're directly related. In this experiment, we'll also have to make use of the relationship between pressure and volume, and that's described by Boyle's law. Boyle's law tells us that volume is inversely related to pressure. Look at the person about to go snorkeling. The average adult has a lung capacity of about 10 pints at atmospheric pressure. If then we dive to a depth of 33 feet, that would double the pressure, and the volume of the lungs decreases by a factor of 2 because we increase the pressure by a factor of 2. All of us have had a soft object in our hand at some point that we squeezed and it got smaller. That's the relationship. Now, this is often demonstrated by a gas syringe like you see here. So if you withdraw the plunger and get 60 milliliters of air at 1 atmosphere pressure, representing this first point, then you seal the syringe and depress the cylinder so the volume is compressed down to 30 milliliters. You've decreased the volume by a factor of 2. That would require twice the pressure. You've increased the pressure by a factor of 2, and that decreases the volume by a factor of 2. Similarly, if the plunger was depressed so that the volume decreased from 60 mils down to 20 mils, then the volume decreased by a factor of 3. And the pressure required to do that would be 3 times as much. It would be 3 atmospheres. So if the pressure increases by a factor of 3, the volume decreases by a factor of 3. And similarly, if 60 mils of gas is compressed to 15 milliliters, that's a 4-fold reduction in volume. That would occur with a 4-fold increase in pressure. That's Boyle's law. Now, how do we solve problems involving pressure and volume? Well, we do it the same way we did for temperature and volume, using simple, logical common sense. So here is the versatile, logical, foolproof method of problem solving that you should always use. Let's take an everyday non-school example so you can see how you solve problems when you're not memorizing formulas, when you're not at school. And we'll do it the same way now at school. A student commutes from home to college each day. He drives his car at a speed of 50 kilometers per hour. His travel time is 30 minutes. What is his travel time if he rides his bicycle at 25 kilometers per hour? Will it be more or less? Let's write the data down. 50 kilometers per hour takes 30 minutes. The bicycle at 25 kilometers per hour, well, you know it's going to take more time because he's going slower. To solve for x minutes, start with the time that you're given, 30 minutes, and multiply by a ratio of speeds that makes sense. Now, it makes sense that you should put the larger speed over the smaller speed because you know it's going to take more time. The ratio is 50 over 25, a factor of 2 to 1. So if you're going half the speed, 25 kilometers is half of 50, it's going to take twice as long, so put 50 over 25. The ratio is 2 over 1. 30 minutes becomes 60 minutes. When you travel the same distance at half the speed, it takes twice as long. Another inverse relationship. How long is his travel time if he jogs at 10 kilometers per hour? It's going to take a lot longer than driving the car. At 50 kilometers per hour, it took 30 minutes. Jogging at 10 kilometers per hour is going to be a lot longer. How many minutes? Start with minutes, multiply by a ratio of the velocities that makes sense. It makes sense that the time has to increase, so put the larger velocity over the smaller velocity. A ratio of 50 over 10 is 5 to 1. 5 times 30, 150 minutes. It's like 2.5 hours. It's going to take 5 times longer because you're traveling 5 times slower. See, there's no magic formulas to memorize. Just use common sense. It's foolproof. You'll always get it right. You notice that the units cancel, right? You start with minutes, you wind up with minutes because the velocities cancel. Let's try a second problem. I'll need a little bit of your grace here. This is a good example, but it's not perfect. A Toyota Echo with a 1.5 liter engine gets 50 miles per gallon, fuel mileage. Estimate the fuel mileage of a BMW with a 3.0 liter engine. Now I know that engine size is not the only factor that affects gas mileage, but it is in fact the major one. So let's just assume it is for the sake of the problem. It is true that cars with larger engines get lower gas mileage. They can't travel as far as a small engine car on a gallon of gasoline. So here's our data. 1.5 liter engine, 50 miles to the gallon. 3 liter engine, it's going to be fewer miles per gallon. So X would be equal to, start with what we're given, 50 miles per gallon, because we're trying to solve for miles per gallon. Make a ratio of the engine size that makes sense. It makes sense that the mileage will be less, so put the small engine size over the large engine size. The factor is 1/2, or a factor of 2. The fuel mileage will decrease by a factor of 2. Now here's an example that is accurate and correct. The average lung capacity or volume of an adult is 5 liters. Previously we said 10 pints. That's the same as 5 liters at 1 atmosphere pressure. If the person dives to a depth of 33 feet in a lake in fresh water, the pressure increases to 2 atmospheres. What is the lung volume of a person at this depth underwater? You don't need a formula. Just use logical statements and common sense. At 1 atmosphere, lung volume is 5 liters. At 2 atmospheres, it's going to be less. So X liters is equal to, start with 5 liters, multiply by a ratio of pressures that makes sense. It makes sense that the lung volume will decrease, so put the small pressure over the large pressure. 1/2 of 5 is 2.5. So in this experiment, the molar volume of hydrogen gas will be determined by collecting and measuring the hydrogen produced in the following reaction. We'll take some magnesium metal, mix it with hydrochloric acid aqueous. The magnesium will be oxidized to magnesium chloride. The hydrogen ion from the acid will be reduced to hydrogen gas. Before we actually look at the reaction, there's one more thing I need to explain. In our experiment, we'll take a graduated cylinder and pour in some dilute aqueous HCl. Then we'll fill the graduated cylinder to the top with water and cover it with a piece of parafilm, which is like stretchy wax paper. We'll try to avoid having any air in the graduated cylinder. Then we'll carefully invert it below the surface of water in a beaker, not allowing air to get in. We'll drop a piece of magnesium metal to the bottom of the beaker and then slide the opening of the graduated cylinder over the magnesium to trap it. As the magnesium reacts with the hydrochloric acid, bubbles of hydrogen gas will be generated and they'll rise to the top. When all of the magnesium reacts, we'll have collected a pretty good volume of hydrogen gas in our graduated cylinder. We need to measure the volume of that. We want to take the measurement when the level of liquid in the beaker is the same as the level of liquid in the graduated cylinder. So you need to raise or lower the graduated cylinder and perhaps you have to add more water to the beaker, raise or lower the graduated cylinder until the level of liquid is the same in the beaker and in the graduated cylinder. And at this point, the atmospheric pressure pushing down on the liquid is the same as the pressure inside the graduated cylinder. If these two liquids are not at the same level, the pressures are different, and we need the pressure of the gas in the cylinder, and we can measure atmospheric pressure with a barometer, so if these are equal, I know the pressures are equal. There's one more thing to explain here. The gas that's inside this graduated cylinder, even if no air was allowed in, it won't only be hydrogen, there'll also be some water vapor present. It is inevitable that any time you collect a gas over water, there'll be some water vapor present. Now, why is that? Well, think about it. When it rains, where does the water go? Water evaporates. It evaporates well below the boiling point, so at any temperature, there's always some water evaporating. Here's a table that shows the vapor pressure of water at various temperatures. So, for example, at 20 degrees C, the vapor pressure of water is 17.4 millimeters of mercury. Notice that as the temperature increases, the vapor pressure of water increases. It evaporates more quickly. As the temperature gets colder, there's lower vapor pressure of water. Water evaporates more slowly. So with this information, we're ready to perform the experiment. This is magnesium metal ribbon. The procedure asks us to weigh up between 0.17 and 0.2 grams. Looks like we're close. I'm going to use emery cloth to remove the oxide layer from the surface so that we are weighing only magnesium and not magnesium plus magnesium oxide. It looks like we're close. I'll get the final mass after I coil it. .16 grams. You should record that number. I've got about 700 mils of water in the beaker. This is 4 molar hydrochloric acid. I'm going to add 50 mils of this to that 250 mil graduated cylinder. Then I want to top that up to the very top with water. I'm going to speed this up to save us some aggravation because I'm adding it slowly to minimize the mixing of the hydrochloric acid and the water. I want to eliminate all the air if possible. This is a piece of parafilm. It's like stretchy wax paper. And I'm going to pull it tight. Looks like I have a couple of milliliters of air, but that's not going to be significant. It'll be negligible, I'm sure. I have to invert this carefully and immerse it below the liquid surface without letting any air in. Success. Now I have to pull the parafilm off. Forgive my hand obstructing your view. All right. Here's our magnesium ribbon. Doesn't want to sink. Okay. Now we want to carefully lift the lip of the graduated cylinder and place it over the magnesium. It's already reacting. See the hydrogen lifting the piece of magnesium to the surface. The magnesium is being oxidized to magnesium ion, and in the process is reducing hydrogen ion to hydrogen gas. We have to wait until that reaction is complete. That'll take a few minutes. I'm speeding this up a bit for you. That's a good volume of hydrogen. Okay, we're just about done. Pretty much done. Looks like approximately 160 milliliters of gas there. Now I need to make sure the level of liquid inside the graduated cylinder is the same as outside, and I'll do that by just adding water to the beaker. Once the levels are the same, I'll take the final volume measurement. Okay, so that's pretty much 160 milliliters of volume. We'll go to the procedure now and look at the calculations required for this experiment. Okay, please follow with me on these calculations. There are a few of them. So atmospheric pressure, also called barometric pressure, varies with the weather and the elevation. And standard atmospheric pressure is defined as 1 atmosphere, or 760 millimeters of mercury at sea level on a clear day. Now Windsor is not at sea level. It's 177 meters, or 581 feet above sea level, so the barometric pressure in Windsor is typically less than that at sea level. Let's say, for example, we had 740 millimeters of mercury on a clear day. We want to calculate the pressure of hydrogen. Let's assume that room temperature was 20 degrees Celsius, or 293 Kelvin, and we'll use atmospheric pressure at 740 millimeters of mercury. From the vapor pressure table on the previous page, the vapor pressure of water at 20 degrees Celsius is 17.4 millimeters of mercury. So we can write that the atmospheric pressure, which was the pressure outside the cylinder, is equal to the pressure inside the cylinder, which was also at atmospheric pressure. But inside the cylinder, the pressure was due to hydrogen plus water vapor. We want to calculate just the pressure of the hydrogen. Let's rearrange the equation. We'll say the pressure of the hydrogen is atmospheric pressure minus the vapor pressure of water. So the pressure of hydrogen in this example is 740 millimeters of mercury minus 17.4 millimeters of mercury of water vapor pressure is 722.6 millimeters of mercury. That's the vapor pressure of hydrogen. We want to also calculate the number of moles of hydrogen. So we have the mass. In this example, it's 0.2 grams. If we divide that by the molar mass, grams divided by grams per mole gives us moles, divided by 24.35 is 0.00823 moles of magnesium. From the stoichiometry of the equation, 1 mole of magnesium produces 1 mole of hydrogen, and therefore 00823 moles of magnesium produce 00823 moles of hydrogen. Later on we're going to want the mass, so let's get it now. If we multiply the number of moles times grams per mole, we get grams. So 00823 times the molar mass of hydrogen, 2.016 grams per mole, gives us 0.0166 grams of hydrogen. Next we want to solve for the volume of hydrogen at STP. STP is standard temperature and pressure, which is 0 degrees C, or 273 Kelvin, and 1 atmosphere, or 760 millimeters of mercury. So V2 will be that volume of hydrogen at STP. This will be our experimental volume. We'll multiply our experimental volume at our conditions times a ratio of pressures and temperatures to convert it to what the volume would be at STP. So please follow with me here. Assuming 0.2 grams of magnesium produced 200 mils of gas at 20 degrees Celsius, and the barometric pressure was 740 millimeters of mercury. Now don't forget, we already determined that the pressure of hydrogen is not 740, but it's 740 minus the vapor pressure of water, so that'll be 722.6 millimeters of mercury. Here's our experimental conditions. V1 is 200 mils. P1 is 722.6 millimeters of mercury. T1 is 20 degrees C, or 293 Kelvin. At STP, we want to calculate the volume. Pressure at STP is 760 millimeters of mercury. Temperature at STP is 0 degrees C, or 273 Kelvin. So start with the volume at experimental conditions, 200 mils. Multiply it by a ratio of pressures that makes sense. Now think about it. If the pressure is increasing from 722 up to 760, that would decrease the volume. So to calculate the new volume, make the ratio such that the smaller number is over the bigger number. The increasing pressure will decrease the volume. Now we have to compensate for temperature. Experimental conditions is at 293 Kelvin. We want to calculate the volume at standard temperature of 273. 273 is colder than 293. Cooling the gas will make it smaller. So again, put the smaller number over the larger number. Make the volume reduce by the same factor by which the Kelvin temperature reduced. When you combine these calculations together, we find that the volume of hydrogen at STP would be 177 milliliters, or 0.177 liters. From this, we want to calculate the molar volume of hydrogen from our experimental data. We saw that at STP, 0.00823 moles of hydrogen would occupy 0.177 liters. Well, how much would 1 mole occupy? Well, more than this by this ratio. 1 mole over 00823 times 0.177 is 21.5 liters. Or you could simply use the formula. Molar volume is liters per mole, so divide the number of liters by the number of moles and get 21.5 liters per mole. Next, let's calculate the percentage error. Now, the theoretical molar volume of any gas at STP is 22.4 liters. Percentage error will be experimental minus the true over the true times 100, or 21.5 minus 22.4 divided by 22.4 times 100 is negative 4% error. Make sure that you include the negative sign if it in fact is a negative error. Let's now calculate the density of hydrogen gas. Density is mass over volume. So 00823 moles, we previously calculated that is 0.0166 grams of hydrogen. That would be our mass. At experimental conditions, 0.0166 grams of hydrogen occupied 0.20 liters, grams per liter, 0.083 grams per liter. When we converted that to STP, the volume changed. The mass didn't, but the volume changed. It shrunk to 0.177 liters. And so at STP, the density is 0.094 grams per liter. Let's finally calculate the percentage error in the density at STP. The true density of hydrogen at STP is 0.090 grams per liter. The percentage error is experimental minus true divided by true times 100, 0.094 grams per liter minus 0.090 grams per liter divided by 0.090 grams per liter times 100% is plus 4.4% error. I want to point out that it makes sense that the density of gas is less at the experimental conditions than it is at STP. So notice the density is 0.083 at experimental conditions, but it's larger. It's 0.94 grams per liter at STP. Why does that make sense? Well, recall that experimental conditions involved a higher temperature, 293 Kelvin, and a lower pressure, 722.6 millimeters of mercury, compared to STP at 273 Kelvin and 760 millimeters of mercury. And we learned that gases expand and become less dense as the temperature increases and pressure decreases. To conclude, let's look at the data sheet you're required to fill out. Please enter your data and results in exactly the same way as you see in the lab procedure. So here is the data that was collected in this experiment. Please use this data in your calculations. The mass of magnesium was 0.16 grams. The temperature of the gas was the same as the temperature of the liquid, 20 degrees C. Atmospheric pressure was 749 millimeters of mercury, and the volume of gas collected 160 milliliters. And that should be sufficient, so that ends our discussion of the molar volume of hydrogen experiment.